Hello, ladies and gentlemen, and welcome to the presentation this morning on the bank effect. My name's Adam Whittle. I'm the marketing manager at Brooks Bell, and presenting today will be Nick Doherty, who will take you through the concept of the bank effect, our use of computational fluid dynamics, or CFD, and also some real-world situations where bank effect can occur. The presentation should last for approximately 40-45 minutes, after which time we'll go to a Q&A. The Q&A function is available by text, so if you write your question using the text facility, I'll put it to Nick after he's finished his presentation. So without any further ado, Nick, I'll hand over to you, and good luck with the presentation.
Thanks, Adam. Yeah, hello everyone. Thanks for joining in. I'm not too sure who's there, but thanks anyway. So yeah, as Adam mentioned, this webinar or this presentation will be on bank effect. So just quickly go over what I'll cover in this presentation. So first of all, I'll just look a quick explanation of what we understand as bank effect, what these are, what these forces are, where they come from. And then we can look at ways of how can we quantify bank effect? How can we measure how large these forces might be? And I will suggest or cover in this presentation one method of doing that by computational fluid dynamics, or CFD. But when we use CFD, we have to bear in mind that it is a computational calculation, and we have to be certain that we are performing these calculations correctly. And the way we do that typically with CFD is to validate our calculations with model test results. So the next stage, I'll just go through a validation study of our calculations with available test data. And then if we have we can be confident from a validation study that we have accurate CFD models. We can use these models to dig in a bit more to look at the reasons for the physical reasons for bank effect forces and where they come from. And then once we have a bit of understanding as about where bank effect forces are coming from, we can look at a bit more complex details that often arise in real world situations, and these would include vessel drift, non-solid banks and uneven channels. And then we can look at quantifying how these bank effect forces in these situations can be modelled in manoeuvring simulations, so how they can affect your manoeuvring of your vessel. And we'll do that with an in-house software, manoeuvring software, which is called BB-Sim. And finally, we'll just at the end just going to summarise with some conclusions of things we've learned, hopefully. So first of all, what is bank effect? So for a vessel travelling, thankfully, which they largely do in unrestricted open water such as oceans, the forces exerted on that vessel are largely very steady and very predictable. So for a vessel moving forward in an open water, all you really have, because of your relative flow to the vessel, you only really have vessel drag acting to push that vessel back. But this is very predictable, very steady, and to counter that, we just apply a propulsion force to maintain your same forward speed. But these are your only forces involved, really, typically. The problem arises in bank effect when you operate not in open water conditions, but in a restricted channel condition. So where you have a channel bank or a channel bottom that is quite close to your vessel. And in these situations, the forces exerted on the vessel become a lot less predictable. So for moving forward, and as we were in an open situation, in a channel bank, you'll still have vessel drag, which you still need to counter with propulsion. But you also have these other forces starting to come into play, which act on the side, which is known, or act in the lateral direction. And this is known as vessel sway force. And you also have this kind of twisting force that acts to turn the vessel off its course, which is known as the vessel yaw or yaw moment. And it's these two forces, the sway force and the yaw moment, that we associate typically with bank effect. As mentioned, how can we measure how large these forces could be? How can we quantify these forces? And as I mentioned, the one method that I would suggest and that I use commonly is through computational fluid dynamics, or CFD. And what CFD does is it fundamentally solves your fluid flow equations. And because you're fundamentally solving those equations, it allows you to model and simulate any geometry where fluid flows around, and it also allows you to model any fluid type. So this opens it up to being capable to solve for a wide variety of applications, which we actually do use it for in Brooks Bell, and some of them are shown in the left here. And the top left is one that's particularly relevant to what we're looking at today. We do a lot of hull design calculations where you essentially model your exact geometry of your hull. You put it into your operating condition, how it would operate in real world conditions. And you calculate the resistance force generated in operation. And once you have a resistance force of your hull and how well that hull is performing, you can start to tweak your hull and optimize your hull and perform optimization studies so you improve your performance of your hull. So this is something we do quite regularly. And we also do a lot of aerodynamic studies, so wind coming over your superstructure, and that can be used for applications, as you see in the bottom image, for how well a funnel performs, for example, so how well your smoke can clear or not from your superstructure. Now CFD is continually improving and advancing and improving on its capability and what it can solve. So nowadays you can get some very advanced simulations and a very complex interactions such as propeller-rudder interaction, which you see at the top. This animation here in the middle, which hopefully you can see running, is for a bow thruster, which we were interested in this case in the forces being exerted as a result of vibration because of turbulent flow on your thruster blades. And so you can output forces at any point in your solution. In this case, it was on the thruster blades. And for different physical geometries, you can assess how that affects, in this case, vibration forces acting on that thruster. And the bottom one, which is hopefully running also, is a tank sloshing case. And this again is quite a complex issue where you have vessel motions impacting how the tank sloshes, and then vice versa, the tank sloshing can influence the vessel behaviour. So it's quite a complex interaction which can be modelled quite accurately with CFD. So these are just a few. As I say, we use it for a wide range of applications. It's just an example of a few of them that we have and do use it for. So you can see that it can lend itself quite well to what we are interested here in this presentation, in bank effects and how we can. But as I mentioned, it is a numerical calculation, so we have to perform a validation, and the way to do that typically is to compare it to, if available, any model tests. And for bank effect, we're quite fortunate in that there is a very recent study performed by Flanders Hydraulics Research, where they looked at bank effect forces occurring on the KVL CC2 vessel. Now, the KVL CC2 vessel is an open source benchmark vessel. It's not a real vessel, but it's a hull form that's used by people like myself and model test facilities to check that their processes are accurate, because the results of your forces and so on this vessel are widely known. So all this data is freely available. We have access to the hull form used in these model tests. We have access to the channel geometries which they perform the tests in. So we can essentially just copy these model tests exactly in CFD. and then compare the safety results to the model test results. And what they've done in the model tests is essentially just look at different, vary the gap between the proximity of the vessel to the channel bank. So they started at 9.8 metre gap between your vessel side and your channel side, and then steadily increased that to 15, 44 and 58 metre gaps. And they've also looked at how the under keel clearance, or the distance between the bottom of your hull and the bottom of the channel, how that distance, varying that distance, can affect your bank effect forces. So they started at 7 metre clearance, decreased it to around 2, and then increased it to around 10 metre clearance. And for all of these tests, they performed these for a 6 knot full scale speed, which is a Froude number for this vessel of 0.055, and a model scale of 1 to 75, or 1/75th of the full scale. And so we can copy that exactly and perform the same tests exactly, and then, as I mentioned, compare the forces that we get compared to what they reported in the model tests. And this is what's done here in the graphs on the left. So for the sway force, which is the top left here, you have the model test results in blue and the safety results in orange, and the bottom graph is for your yaw moment, your twisting moment. And so you can see that the CFD and the model tests agree quite well, and this is for varying your distance from the bank, so going from 9 to 58. And for the under keel clearance, similarly, you get quite a good comparison for both sway force and yaw moment. One thing to note in our CFD calculations, there is no free surface effect, so no waves, and that means that there's also no sinkage and no trim effects. This is very possible in CFD, you can do that fine, but just for reasons of quickness in this solution, that hasn't been done. So I think if you included these effects, you could probably get an even better correlation between your model tests and your safety results. But for the purpose of this presentation, I think we have a good correlation. We can be reasonably confident that our model tests are accurately predicting your bank effect forces. So once we have this confidence, we can then look at our model test or our model results and start to dig into answer questions about where these forces come from. And also we can start to look at, when we look at the sway force, we see that with increasing your distance from the bank, you can see that the sway force, for instance, decreases in size, and we can start to answer questions as to why that pattern is observed. And now CFD is something that lends itself particularly well to this investigation aspect, so you can really get into any part in your flow and look at the conditions of that flow. So whatever you've modelled, you can look at velocity, you can look at pressure, you can look at forces, and you can get a lot more information in CFD solutions than you can from something, for example, like model tests. And a very typical way of looking at flow is what's shown here, is to plot your streamlines. So streamlines are essentially just showing your path that the flow is taking around any objects. So it's kind of like dropping a feather or something in the flow, and watching how the path that takes and just tracing that path. So for here, you've got lots of different streamlines as though you've dropped lots of feathers and you're following the path in all these different points. And so it shows your path, but it can also show your speed. And you note that these streamlines are coloured, and they're coloured by velocity, or specifically velocity relative to the vessel. And just a quick explanation of what the velocity scales and the colours mean. So if we look at the far forward of the vessel, where it's largely undisturbed by the vessel, and we look at so it's a kind of light orange colour. If we look at the scale in this, it corresponds to a value of relative or normalised velocity of 1. And that really signifies that your flow field here is not affected by the vessel, which is something we would expect far forward in this region. As we come forward so that it starts impacting the vessel, you start to see the colour changing, and it's turning yellow and green and blue. And if we look in the scale here, we see that these colours correspond to values less than 1, and values less than 1 indicate that the flow is being slowed down. and that's something that you would expect here also, because it's hitting the bow and it's slowing down as a result relative to the vessel. As we come further along, you notice that it's becoming a dark orange and red in some places. And if we look at a scale here, it's actually values of above 1. And these values of above 1 mean that your relative speed is actually, the flow is actually being speeded up or accelerated around the sides. So your relative speed is actually being accelerated around the sides here. And then as we come further aft towards the aft, it starts to slow down again, and you get yellow and greens, and these are below 1, so it shows it's been pulled along slightly from your by your vessel and slowed down. And why velocities are important and why the relative velocities there are important is that velocities are highly linked or intrinsically linked to your pressures of your flow around the vessel, and this is a contour plot of your pressure field. So similarly, it's not streamlines, it's showing your entire pressure field, and similarly, it's plotted in a kind of non-dimensionalized pressure, so it's relative pressure relative to the normal pressure. So if we look in the same areas, look further forward of the vessel where it's unaffected by the vessel, your colour is kind of light yellow greenish, and that's a value of pressure coefficient of 0. And that 0 value signifies unaffected flow, so the pressure is unaffected by the vessel. And as we come forward towards the vessel, you notice this red region, this starts turning orange and red, and if we look at what these values are in pressure, it's a positive pressure, so it's a positive, and if we remember, this was the area of the flow that was being slowed down by the hull. And as mentioned, flow speed is linked to pressure, so as the flow speed reduces, your pressure actually increases, and we see that in the pressure coefficient. And then as we carry on around, whereas we remember the flow is being accelerated and speeded up through around the sides, you notice that the pressure is actually a kind of turquoisey and blue colour. And here, in the scale of pressure coefficient, that's actually negative. It's below 0, so it's tending towards -1, and these negative values signify a negative pressure, so it's kind of suction pressure sucking out from the vessel itself, and that's again a result, much like when you slow the speed down, you increase the pressure. When you speed the speed of the flow up, you decrease the pressure, so you get this negative pressure from high speed flows. And then as we carry on forward, or carry on round aft towards the vessel, it starts to slow down again, and the pressure starts to increase because of your reduced velocities. So you have, if we look at it from the bottom, you have a high pressure region at the bow because you slowed down velocities. As your flow increases speed around the sides, it has a negative pulling or sucking force in the sides. And then towards the aft, we have a positive pressure pushing it on the aft again slightly. And as you will understand, pressure is linked to force. So if you're applying a pressure on a body, it essentially applies a force on that body. And if the pressure is positive, it's applying a pushing force. So at the bow and the aft, you have these positive pushing in towards the vessel. And at the side, you have these negative forces, negative pressures, creating a pulling force and pulling the vessel out. So for this vessel, this solution we're looking at here is for an open water case, an unrestricted flow. Your vessel is obviously symmetrical, so your flow field around your vessel is symmetrical. And what that means when you start to sum up your flow in the sideways direction and your lateral direction, so you have a positive pressure coming in your port side, but you've got an equal positive pressure acting in the opposite direction on your starboard side. And similarly with your suction forces, what's happening in the port side is equal and opposite to what's happening in the starboard side. And so they kind of balance each other out because your vessel is symmetrical. And so you have no effectively no imbalanced forces. It's all perfectly balanced in the lateral direction. This similarly, any kind of twisting forces are the result of any kind of lateral forces, because of your symmetry of your vessel, what's happening on one side is happening on the other, and the twisting force because of one side is the same as the twisting force because of the other side. So your yaw force is identical and equal and opposite, so that balances to zero, and your only imbalance forces is in your longitudinal direction, so in the forward-aft direction. So if you notice, your pressure field is quite large red towards the bow, so you've got quite a high pushing force at the bow, lower positive pressure force at the aft, so quite a low pressure force at the aft. This creates an imbalance in the aft direction, which, as we looked at before, is just your drag force. So for open water cases, all you really have operating on that is your drag force. You counter that with propulsion, and you have a steady forward motion. The issue starts to arise for when you come away from open water flow. So in restricted channels, where you have a channel bank near your vessel, and you look at your streamlines along through or over your vessel, you start to see immediately that it's very asymmetrical flow. So what's happening on one side isn't the same as what's happening on the other side, and you can also see that the speeds are quite high red. It's kind of intensified your speeds, and as we remember, the speeds are linked to your pressure. So what this means for your pressure field around the vessel, you can see that one, it's very asymmetrical. What's happening on one side isn't the same as what's happening on the other side. You have this high region of pressure on the bow, but it's kind of acting on the port side, which is a pushing force more towards port side. As we travel further down the side, you get regions of high dark blue or deep blue, and that's a high negative pressure. So you get a really high sucking force at the side between your channel and your vessel. You have a sucking force on the starboard side, but not the same magnitude. And when you sum up all these in the lateral direction, you begin to see that you have pushing force towards the starboard side at the bow, high sucking forces towards the port side, down the sides. And you sum these up and you see that the imbalance in the forces acts towards the port side, or towards the channel. So you essentially have a pulling or a sucking force pulling that vessel in towards the channel bank. And that's just sway force associated with bank effect, and that's a result of your pressure field around your vessel. And similarly, when we look at the yaw moment on the vessel, this is a result of your imbalance in your forces. So you've got this pushing force at the bow, sucking force further aft, but overall it's kind of pushing it round as we look at it anti-clockwise. So it's kind of pushing the bow away from the bank and pushing the stern towards the bank. So you have these two forces which we associate with bank effect, pulling it towards the bank and turning the orientation of the vessel away, port side, bow towards the starboard, away from the channel bank. So we have a physical understanding of where the bank effect forces come. You can see it's from your asymmetry of the flow, which is causing these pressure conditions around your vessel, and we understand now what directions your bank effect forces are occurring in, and now we can start to look at why, for instance, is there a reduction in your bank effect forces, both in sway and in yaw moment as you come away, or increase the gap between your vessel and your channel bank. And we can do that. We can investigate that similarly by looking at the pressure plots. So you can see immediately that as you so the far left here is for the small gap, the 9.8 meter gap, and as we come along towards the higher gap, the 58 meter gap, you can see the intensity of your pressure field is reducing. So this causes a reduction in your imbalance. You can also see at the 58 meter case, it's getting towards, it's not completely symmetrical flow, but it's getting towards symmetrical flow, which we saw in the open water case. So that imbalance reduces because of your reduction in pressure intensities, and it's becoming more symmetrical as you move away from the bank. And similarly, it's when we look at the imbalance in your positive and pressure forces combined, which affects your yaw, you can see that for the small gap, you've got this high region of high pressure at the bow, but it's acting very much at an angle towards on the port side. And as you come away from the bank, it starts centering itself. It becomes a bit more symmetrical down the centre line. And that all combines so that you have a reduction in this yaw moment as you come away from the bank. And so we have a physical explanation based on the pressure field. And as I mentioned, as you would probably expect, this is a result of your asymmetry in your flow, or how your flow field is affected. So you can see as you come from 9.8 metre gap on the left towards 58 metre gap, the flow field is becoming a lot more symmetrical and a lot less imbalanced, and that affects, as we just saw, the pressure region. And so that explains why a bank effect reduces as we come away from the bank. So now that we hopefully have a bit more understanding about where our bank effect forces come from, bear in mind what we've been looking at here are very idealised conditions. We've been comparing it all to model test results, and these are everything is nice and perfectly geometry, nice smooth channel banks. So that's interesting or useful to learn and get an insight into what bank effect comes from. But in real world situations, it's often much more complex and much more messy. And one of the things that makes real world situations complex is that you'll almost always have vessel drift in manoeuvring cases, particularly when it's operating in a channel in restricted waterways. So what vessel drift is if your vessel is actually travelling along the red arrow there and straight on up, but it's oriented slightly differently. So the vessel is actually oriented along the green arrow. The drift angle is the difference between your travel direction and your vessel direction. And as I say, this is very common, and so it's important to understand if this has an effect. You'll almost always get this in real world situations. So what we've done to study this is just look at various different drift angles. So -10 towards the starboard side, then -5, 0 we already have, and then we've done mirror image towards the port side. And just for these drift angles, just go through the exact same tests as we've looked at before. For the no drift case, and immediately when you start plotting your flow structure around your vessel, you see you have asymmetry purely as a result of your drift angle. So for these plots, it's all in open water. The only influence is your drift angle. So you have high asymmetry in your -10 direction there, less so in your 5, and then the mirror image in your +5 and +10. And these asymmetric flow conditions, not so dissimilar to what we were looking at in the bank effect cases. And these also affect your pressure fields, as we would expect. And when we look at the pressure field, we see that we have a similar kind of a pressure field that we kind of recognise from what we were just looking at for bank effect. So you have this high pressure region at the bow, but it's acting on the kind of on the starboard side and the -10 drift angle. And then as you come around your starboard side, you have this high negative pressure region or negative pressure values around the side as it's being speeded up around your starboard side. And then it's you've got high pressure region at the aft, and these cause similar forces to occur on your vessel as we saw with bank effect. You've got a kind of sway force acting on because of these pressure fields, and you've got a twisting force or a yaw moment, and it's more intense as you increase your drift angle. So the question arises, or we can see that these could possibly combine with with bank effect forces when you're operating in a restricted channel. And so if we look at drift angle cases in a restricted channel, you see that that is indeed the case. So this image on the left is what we've just been looking at for open water for -5 degree drift angle. But the image in the middle is the same drift angle, but in a restricted channel. And you can see it's just a huge kind of intensification of your asymmetry, but also you've got a lot of speeded up flow there that's not evident in your open water channel. And also if you compare it to the restricted channel case with no drift angle, which is the image on the right, you see that the drift angle is just much more asymmetric and it just looks more intense. You know, it's much more fast flow occurring there, and it's much more asymmetric and much worse looking. And what that means for the pressure field, which is kind of all important for forces, is just as we would expect. You know, you have this massive intensification of pressure field. So you get much more deeper blues, and you've got a much larger region of red at the bow on the port side there. And so as you would expect, this is for a positive drift angle. So, but you see a similar thing, not the same pressure field or not the same places where the pressure field is occurring, but a large intensification of your values of pressure there. And that's the combination of your restricted channel, your bank effect, and your drift angle. And as we would expect, that significantly affects your forces. So if we compare, the black line is for varying your drift angle in an open water channel, and your dotted blue line there is for varying your drift angle in a restricted channel. But this is actually for quite a far away case. So the channel is like 44 meters away, but you can see that there's a marked difference in your forces, in your sway force and your yaw force, even at this high or large gap case. And if we look at all of the gap cases together, you can see it just gets much worse as you decrease the distance between the vessel and the channel bank. So what we saw with this intensification of your pressure field is realised in your forces, and so you get much larger sway forces and yaw forces when you have drift angles included. So this is obviously can cause huge problems for the manoeuvring of the vessel, particularly if it's closer to a bank. You get these large forces, and they can often be responsible for the accidents that we see. So another complicating issue often comes up in real-world situations is a non-solid bank. So these often occur in jetties and piers where it's a series of concrete pillars. Essentially, you don't have a solid wall at the side. But we often do see accidents in these around these piers, and the question in these cases can arise: was bank effect significant? And people may argue that it's not significant because it's not solid. Now, knowing or getting data on whether that's the case or not, there's no experimental studies that I've been able to find, all kind of model tests of solid walls. So it's very difficult to definitively say, based on any kind of data that's out there, or these can or these do or do not have an effect or bank effect as at play here in non-solid geometries. So the only real way you can do it is to perform a build a model yourself, which is what we've done here. And we've looked at two different bank values of solid banks. So you've got 50% solid and 25% solid. So the 50% solid is kind of as open as it is, so it's closed, and then just increasing the openness. So you've only got 25% solid bank there. And then we've just performed the same studies as we looked at there. And that allows us to compare the forces and the pressure fields around the vessel for your solid bank, which is your top row there, your 50% solid bank, which is your middle row, and then your bottom row is your 25% solid bank. And you can see, as we might expect, that as we come down to the less solid banks and the more open banks, that the intensification, your pressure field is just slowly reducing in intensity. And that's something that might be quite intuitive and quite something we might have expected. But we can also see that it's not, the bank effect is still there, because we can still see that there's asymmetry in the pressure field. Even at the 25-degree and 25% solid cases. So we can see that bank effect is being reduced, but it's not disappearing, so it still can play a part. But what's also of interest here is that although your intensity is reducing, it's not reducing uniformly, so you don't have the same pressure field patterns as you go from 100% solid bank to 50% solid. So if we look at the top, the far left column, the 9.8 meter gap, and we look at the 100% solid gap in the far top left, you have this high, deep blue region towards the forward of the vessel at the side here. But as we look at the 50% solid case, the deeper blue region is more towards the aft. It's not the same position. So things are kind of changing. It's not exactly the same, even though it's reducing. And if we look at what this all means for the forces acting on the vessel, so the blue line is for the solid bank, the orange is for the 50%, the green is for the 25% porous bank, and then the red dotted line is for the open water. And you can see for sway force, this gradually, your sway force does gradually reduce with how solid your bank is, which is something we expect or we can understand from the reduction in the intensity of your pressures around your vessel. But the interesting thing to me in this one is the results of your yaw force. So you see that for the solid case, it's a negative value, which indicates the direction that it's going, but the magnitude of your yaw force is actually much lower for the solid bank than it is for the porous banks, the non-solid banks. So your solid bank yaw moment is closer to your open water case than your non-solid banks, and this is very surprising, and it makes you question, could that be correct? Because it's not what you would expect. You would expect a reduction, as we saw in the sway force. And if we look back again at our pressure fields, and we can start to get an understanding of why this is the case. And it's back to what I was just explaining earlier, this difference in your pattern of your pressure field. So if we look at the top left here in your solid field at your solid bank at 9.8 meters, you've got a high positive value at your bow. So that's turning your bow away from the channel, but your high negative, your deep blue region, is also near your bow, and that's pulling the bow back in towards your bank. And this isn't the case in your 50% case, so you get your same high pressure force at the bow, which is pushing it away from the bank, but your low pressure field doesn't happen until you're towards the aft, which is similarly pulling your aft in and pushing your bow out. And this is all, so it's not, your yaw force isn't countering each other, it's actually, the pressure field is actually combining to complement your, or add to your yaw moment. And this is why for 50% solids cases, your yaw moment is actually higher than your 100% solid case. So that's something that's very interesting, something that we wouldn't have expected until, certainly something that you couldn't have picked up from any kind of model tests without actually modelling your non-solid cases. And that is potentially large implications for accidents that happen at pier. It's not a reduction; it can actually increase when you have a non-solid bank, and increase how much the vessel is being turned off course. So another almost universal problem in real world cases is uneven channel depths. And this is very typical in really anywhere a vessel is operating in a restricted channel. So for riverbanks, the channel depth is constantly changing, but that would be true in ports also. But this is a case we're looking at here of a riverbank being modelled, and it's the contours here are showing variation in depth, and you can see there's huge variations in depth. So your vessel is constantly at different points in that riverbank, travelling over a different depth of river. So the proximity of the keel or the hull to your riverbank can change quite rapidly. And the question will arise, can that have an effect on any forces around the vessel, such as bank effect forces? And if we remember that the Flanders model test study actually looked at this, they looked at the variation in bank effect forces with under keel clearance. So we can get an idea of what we would expect from these model tests, and we can see that as we decrease your under keel clearance from 7 meters to 2 meters, you get a huge, you get a change in your actual direction of your sway force. So it's actually going from pulling it towards the bank to pushing it away from the bank. You see it's turning from positive to negative. But in the yaw moment, you get just a huge increase in your actual magnitude of your turning force. So when you go from 7 to 2 meters in your yaw moment, which is the bottom diagram there, it's like 10 times higher than it was at 7 meters. So you can see that it's an order of magnitude higher than just by reducing your under keel clearance. And so you can see that when you start applying that to real world situations, that could potentially be very significant. And if we just explain quickly why that occurs, so this is your streamlines in your 2.1 meter clearance case, and you can see that in the far left is 2.1, and you compare that to the 7.3 in the middle. You can see that there's very few streamlines actually going underneath the keel, and that's because there's just a far smaller gap there. Flow can't get in there to go through. So if it can't go through underneath the hull, it has to go somewhere else. And what happens is if it goes somewhere else, it largely goes around the sides of the vessel. So you have this intensification of your flow around your vessel. And for the pressure field, that just means an intensification of your pressure field towards the sides of your vessel, which you can see immediately when you compare the pressures between 2.1 and 7.3. And that obviously just leads to these high or marked increases in your pressure forces or your bank effect forces. And so when we consider if a vessel is constantly changing its under keel clearance, and you get these huge variations in your bank effect forces as a result, that can have huge implications on your yaw moment particularly. So if you go over a particularly shallow part of the river, you can have a quite sudden yaw moment that's suddenly 10 times higher than it was previously, and that can obviously have impacts on the manoeuvring of the vessel and if the captain isn't expecting these kind of forces. Which for real world situations, we often want to know how does that affect the manoeuvring ability, or how the manoeuvring of the vessel was affected. In this case we've been looking at with the channel, the river channel was something we actually looked at for an incident that occurred. And what we did to do that was model the river and model the vessel at various points along that river and monitor the forces in CFD. And then we can plug these forces into the Manoeuvring Simulation software, BB-Sim. And we can see with the manoeuvring software how these forces affected your manoeuvre of the vessel. And so what we did in this case was we applied a manoeuvre without these forces included, these forces due to your changing channel depth. And I hope this is clear enough. This is kind of yellow outline of this was the manoeuvre without these forces. And this is using the actual rudder commands issued by the captain when he was trying to berth onto the jetty. And if you didn't have these extra forces included, the rudder commands actually performed this manoeuvre really very nicely so you had a nice smooth berthing manoeuvre onto the jetty, and it came out nicely parallel and lined up perfectly with the jetty. But when you included these bank effect forces, or these increased forces, this is the red, and then we performed that manoeuvre with these included, and that's in the red outline. And this is, so that what it actually did was turn that vessel around because of your increased yaw moment. And this is, and it followed a trajectory that actually occurred in the incident. And what happened in the incident is it was turned around and damaged and kind of collided with the jetty at the bow and damaged the vessel and the jetty itself. And so we could get a very quite an accurate representation of the incident and an explanation of why that incident occurred. From doing CFD and then applying it to the manoeuvring model. So just in conclusion, there are, as we've seen, there are published data out there in model tests. The issue with model tests and learning from the data there is it's all very idealized and configurations, so that it's when you then compare or use that data to real world conditions, when you've got messy issues such as vessel drift, non-solid piers, varying channel depths, and often a combination of all of those things, the usefulness of these model test data becomes a bit less clear, and you can actually often rely, if you rely entirely on those, you can come to some wrong conclusions. Which is something we saw with the yaw moment increasing as you reduce the porosity or reduce the solid bank. It's something that you wouldn't pick up on relying purely on model tests, is that you can actually increase your yaw moment when you have a non-solid bank. And so the forces that occur on your vessel are highly individual to the vessel and to the situation that it was operating in. So the only way you can really do that is by modelling or recreating that situation exactly, and that includes all geometries important to that situation, including your vessel hull and your channel geometry. Another interesting thing is that manoeuvring models typically use coefficients for geometries only bulk carrier vessels. So if your vessel is not a bulk carrier, the manoeuvring simulations are often not relevant to or not accurate to that vessel. So, but you can make that accurate if you model your hull and CFD and then use those forces in the manoeuvring simulation. So you can see the importance of getting things accurately, and the way to get things accurately is to recreate your situation as clearly as possible or as accurately as possible. So hopefully that's been of interest, and I've covered most of the issues with bank effect, but if you have any questions, now would be the time to ask. But thanks for listening.
Okay, thanks, Nick. So we have one question in, and it's regarding the FHR study and the validation graph correlation. And it's how close does quite close have to be acceptable, and how do you define confidence?
Yeah, good question. So can I go back to it? Yeah, it's a difficult question. Really, what gave me confidence in this one, you're not getting an exact match, and which is probably where the question arises from, but you do have you see the patterns are following each other. So you have the same, for different configurations, you have the same pattern, but you're never going to get an exact match between, even if you performed the same test twice in the model test, you would never have an exact match. What you look for is a reasonable correlation, and correlation often shows with patterns and how that variation affects with different configurations. So it's something that will come up, how accurate your calculation is, and so you'll never have an exact match, as I say. So you always have to look for as good a comparison as you can get as possible. But as I say, if you perform the same tests and model tests twice, you would never get the same result twice as well. It's just one of the problems with comparing. You don't expect a great result, a great perfect match, but you do look to get something close, and particularly your patterns and how your correlations stick together is what I was looking for there.
Okay, thanks, Nick. I hope that answers the question. We're running out of time here now, so if you do have any further questions that you think of later on in the day, or just please email them through to marketing@brooksbell.com, and I'll make sure that they're passed to Nick and he can answer you. This presentation will be posted on our YouTube channel, and we'll send the link out to that for those that want to catch up on it, or those who missed it can catch up later on. But for now, Nick, thanks very much indeed. Ladies and gentlemen, thank you for joining us today, and we'll be in touch again soon. Thank you.
Thank you.